Hi there! I'm going to take you along into the world of organic photodetectors, and more specifically cavity-based organic photodetectors to detect near-infrared light. Detecting near-infrared light is absolutely crucial for a wide range of applications, such as food sorting, but also the cameras in modern smartphones use it for facial recognition. Additionally, when applied into cars, these types of sensors can automatically detect the pedestrian and stop the vehicle in time before accidents happen. From a biomedical standpoint of view, these types of sensors can be used to study brain activity, but also to study specific diseases such as cancer and heart diseases. Additionally, they can also be used to detect viruses. The sensor that I use, a cavity device, consists of two reflecting electrodes, one semi and one non-transparent. Importantly, depending on the distance between these mirrors, photons of a certain wavelength will result in the formation of a standing wave. Simply put, photons of a certain wavelength will be trapped inside the device until they get absorbed by the active layer and result in a narrow detector signal. The active layer is the main focus of my PhD project, developing suitable materials that absorb the desired wavelength and function as a light-absorbing species inside this type of detector. The active layer in its part consists of an acceptor material, in this case PCBM, and a polymeric donor material, which functions as the main absorbing species in the active layer. In order to absorb lower energy near-infrared light, two main material design criteria need to be considered: the electronical and the morphological properties of the material. When this material absorbs light, two types of transitions are possible. Either the indirect charge transfer transition of the electron from the HOMO of the donor to the LUMO of the donor, followed by a charge transition of the electron to the LUMO of the acceptor. This transition is commonly used in non-cavity-based organic photodetectors. Apart from that, there is also a very weak direct charge transfer transition of the electron straight from the HOMO of the donor to the LUMO of the acceptor. Increasing the electron richness of the polymer, hereby raising the HOMO of the material, reduces the direct charge transfer gap. Lower energy photons will be absorbed and extend the charge transfer absorption to longer wavelengths. Further increasing of the HOMO, however, results in a general decrease of the signal, and the explanation can be found in the second design criterion for materials in cavity devices. As a charge transfer transition is a biomolecular transition, the proximity of these materials is crucial in order to make the absorption relatively efficient, and this is extensively studied in collaboration with the group of Nico van den Brande at the VUB. The material on the left is still very intimately mixed with the PCBM acceptor, while the material on the right loses this desired property. Within my project, these materials were obtained after a still polycondensation polymerization, yielding the benchmark material on the left and the novel materials in the middle and on the right. But how can we use this weak charge transfer transition efficiently? This is where the cavity device comes in. Photons are trapped inside the device until they are absorbed by the active layer, resulting in a highly efficient narrow response of the photodetector. This can then be easily shifted to longer wavelengths when increasing the thickness of the active layer between the electrodes. This makes cavity-based organic photodetectors especially interesting for spectroscopic applications, in which photons of a certain wavelength need to be detected over a broad range. Additionally, due to the use of organic materials, thin, flexible detectors are attainable. The current demand for miniaturization and integration of sensors into small devices, or even incorporated into the human body, could potentially be answered through the use of these types of sensors. So, maybe in the future, cavity devices will be used to monitor your body activity.